February 24th, 1943. Buna Airfield, New Guinea. Lieutenant Clyde Gessel stared at the wreckage scattered across the muddy runway. 5 Japanese fighters, twisted metal and torn fabric, but somehow still holding secrets that were killing Allied pilots every day. For months, American P-40 Warhawks and British Hurricanes had been carved apart by nimble enemy aircraft, executing impossible maneuvers. Double Immelmann turns, hammerhead stalls that defied physics. Everyone called them Zeros, but Gessel knew better. These weren't the carrier fighters from Pearl Harbor. These were something else entirely, something the Allies didn't understand. In the twisted wreckage, he saw salvation, enough intact parts to rebuild one complete aircraft. Engine cowling from this one, wings from that one, control surfaces from the third. What Allied intelligence dismissed as primitive copies of Western designs, Gessel suspected were engineering masterpieces built on completely different principles. 6 months later, inside Hangar 7 at Eagle Farm Air Base, American test pilot Bill Ferrier would strap himself into the cockpit of a resurrected enemy fighter. What he discovered would shatter every assumption about Japanese air superiority. The mystery aircraft wasn't just maneuverable. It was something far more dangerous and far more fragile than anyone imagined. The morning heat at Port Moresby was already climbing past 90 degrees when Lieutenant Clyde Gessel stepped off the C-47 transport, his boots hitting the coral dust runway with the kind of precision that marked career engineers. February 24th, 1943 had started like any other day in the Pacific Theater. Radio chatter about Japanese air raids, mechanics cursing over damaged Allied fighters, and another stack of combat reports that made no tactical sense. But the telegram from Australian infantry had changed everything in 43 words. Buna Airfield cleared, multiple Japanese aircraft wrecks recovered. Request immediate technical evaluation, possible new fighter type. Gessel had seen enough mangled aircraft to fill a scrapyard. Since October, when he'd been assigned as enemy equipment engineer for the Allied Technical Air Intelligence Unit, every crashed Japanese fighter had been labeled the same way in official reports. Zero type, origin unknown, capabilities classified. The simplicity was maddening to an engineer who understood that aircraft design revealed everything about enemy doctrine, manufacturing capability, and strategic thinking. You didn't learn to fight an enemy by calling everything they flew by the same name. The jeep ride to Buna took 3 hours through jungle roads that barely deserved the name, past burned-out pillboxes and abandoned supply dumps that marked the recent Japanese retreat. Gessel used the time to review what Allied pilots were reporting from combat encounters across the Pacific. British Hurricane pilots over Burma described Japanese fighters that could turn inside a turning circle. American P-40 crews in China reported enemy aircraft that climbed like homesick angels, but seemed to fall apart after taking any battle damage. Dutch pilots flying Brewster Buffaloes in the East Indies had radioed desperate warnings about Japanese fighters that could execute impossible aerobatic maneuvers before communications went silent forever. The pattern was becoming clear to anyone willing to look past the propaganda. These weren't the same aircraft that had attacked Pearl Harbor. The carrier-based Zeros were formidable enough, but they represented just one piece of Japanese air power. Intelligence reports suggested at least 3 different fighter types in regular combat service, each optimized for different tactical roles. But Allied training manuals still treated Japanese aviation as a monolithic threat, fast, maneuverable, but ultimately inferior to Western engineering standards. Buna Airfield stretched before them like a scar across the jungle canopy, its single runway pocked with bomb craters and littered with the debris of 2 armies. Australian infantry had done their job with characteristic thoroughness. 5 Japanese aircraft had been dragged clear of the runway and arranged in rough formation near the abandoned control tower. Even from a distance, Gessel could see these weren't Zeros. The wing plan form was wrong. The engine cowling suggested a different power plant entirely. The fuselage proportions spoke of an aircraft designed for maximum agility rather than carrier operations. The first aircraft was the most intact, a single-seat fighter with fabric-covered control surfaces, and a radial engine that looked remarkably similar to American designs. Its olive green camouflage was faded but still visible, along with the distinctive red circles that marked Imperial Japanese Army Air Force equipment. The landing gear had been retracted when it crashed, suggesting the pilot had attempted a belly landing rather than a wheels-down emergency approach. Bullet holes stitched across the port wing indicated it had been in combat when it went down. Gessel walked the wreckage line like a detective examining crime scenes. The second aircraft had taken a direct hit from what looked like 20mm cannon fire. Its engine was completely destroyed, but the cockpit and rear fuselage remained largely intact. The third had burned, leaving only the basic airframe structure and a few key components that might still yield useful information. The fourth was missing everything forward of the cockpit, but its wings and control surfaces were undamaged. The fifth had suffered what appeared to be a structural failure. Both wings had folded upward in a pattern that suggested catastrophic G-force loading during a high-speed maneuver. Working methodically through the afternoon heat, Gessel began cataloging recoverable components: engine cowlings, propeller hubs, instrument panels, control cables, fabric samples, ammunition boxes. Each piece represented a fragment of Japanese design philosophy made tangible. The ammunition told an immediate story: 7.7mm rounds in small quantities, suggesting these fighters carried light armament compared to Allied standards. The fabric covering was high-quality linen with distinctive doping patterns that indicated sophisticated manufacturing techniques. But it was the control surfaces that revealed the real secret. Each aircraft mounted what appeared to be split-flap systems that could be deployed independently during flight, not for landing configuration, but for combat maneuvering. Gessel had never seen anything like it on Western fighters. The engineering was elegant and purposeful, designed to increase lift and tighten turning radius during air-to-air combat. It was the kind of innovation that suggested Japanese aircraft designers were thinking about aerial warfare in fundamentally different ways than their Allied counterparts. As the sun began setting over the jungle canopy, Gessel made his decision. There were enough intact components among the 5 wrecks to potentially rebuild one complete aircraft. It would require shipping everything back to Brisbane, requisitioning machine shop time, and convincing skeptical superiors that reconstructing an enemy fighter was worth the enormous effort involved. But the alternative was continuing to fight an enemy they didn't understand, using tactics based on assumptions rather than engineering reality. The telegram he sent that evening was characteristically brief. 5 Japanese fighters recovered. Recommend immediate shipment to Eagle Farm for complete reconstruction. Preliminary analysis suggests new fighter type with unique combat capabilities. Request priority handling. 3 days later, the reply came back with the authorization he needed and a warning that would prove prophetic. Approved. But remember, Lieutenant, understanding the enemy and defeating the enemy are 2 very different problems. Hangar 7 at Eagle Farm Air Base had never hosted a project quite like this one. Built to house standard Allied maintenance operations, the cavernous space now resembled an archaeological dig site, crossed with a precision machine shop. Wooden crates marked "Enemy Equipment Classified" filled one corner, while the center floor had been cleared to accommodate the most ambitious reverse engineering project in Pacific theater history. March 15, 1943, marked the official start of what ATIU technicians privately called Project Phoenix, the resurrection of a complete Japanese fighter from scattered wreckage. Sergeant Mike Kowalski had spent 12 years maintaining aircraft for the Army Air Forces, but nothing in his experience had prepared him for rebuilding an enemy fighter without technical manuals, spare parts, or any clear understanding of Japanese manufacturing standards. The 5 sets of wreckage from Buna had been carefully cataloged and arranged according to aircraft systems, engines in one area, control surfaces in another, instruments and electrical components in a third. Each piece carried a tag indicating its source aircraft and condition assessment, creating a 3-dimensional puzzle with over 2,000 individual components. The engine presented the first major challenge. The Nakajima Ki-43 radial power plant shared obvious design heritage with American Wright Cyclone engines, but crucial differences in cylinder head design and carburetor configuration suggested the Japanese had developed their own manufacturing techniques. Kowalski's team discovered that Japanese tolerances were actually tighter than American standards in several key areas. Cylinder bore dimensions varied less than 0.003 of an inch across all 5 engines, indicating precision manufacturing that contradicted intelligence reports about primitive Japanese industrial capabilities. Working 16-hour days under harsh fluorescent lighting, the technicians began solving problems that no Allied engineer had ever confronted. Japanese control cables used a different wire gauge and tensioning system than American standards. The electrical system operated on a 24-volt configuration that required complete rewiring with available components. Most challenging of all, the unique combat flap system, which Gessel had identified as the key to the aircraft's legendary maneuverability, used a complex mechanical linkage that had to be reverse-engineered from damaged components and educated guesswork. By April, the project had consumed over 3,000 man-hours and attracted attention from Wright Field engineers, who flew in specifically to observe the reconstruction process. The Japanese approach to weight reduction became apparent as each system came together. Where American fighters used steel components, the Japanese substituted aluminum alloys. Where Allied designs incorporated redundant safety systems, Japanese engineers had eliminated every gram of unnecessary material. The result was an aircraft that weighed just over 5,000 pounds fully loaded, nearly 2 tons lighter than comparable Allied fighters. The combat flaps represented the most sophisticated piece of engineering in the entire aircraft. Deployed through a cockpit control lever, they could extend 30 degrees during turning maneuvers to dramatically increase lift coefficient and reduce stall speed. American test pilots had reported Japanese fighters executing impossible turns, but now the mechanism was becoming clear. By deploying combat flaps during engagement, Japanese pilots could maintain controlled flight at airspeeds that would stall any Allied fighter. It was brilliant, elegant, and completely foreign to Western design philosophy. Lieutenant Gessel spent hours studying the cockpit layout, which told its own story about Japanese pilots. Training and combat doctrine. The instrument panel was sparse compared to American standards, basic engine instruments, attitude indicator, compass, and airspeed gauge. No radio compass. No sophisticated navigation equipment. The gun sight was a simple ring and bead arrangement that required considerable pilot skill to use effectively. Everything about the cockpit suggested pilots who were expected to navigate by visual reference and engage enemy aircraft through superior flying skill rather than technological advantage. The armament installation revealed another crucial difference in design philosophy. 2 7.7mm machine guns mounted in the engine, cowling represented the aircraft's entire offensive capability, roughly equivalent to 1/4 the firepower of a standard American fighter. But the ammunition storage and feed system had been optimized for sustained firing rather than brief bursts, suggesting tactical doctrine that emphasized precision marksmanship over overwhelming firepower. Japanese pilots were apparently trained to make every shot count rather than rely on volume of fire to achieve kills. As summer approached, the rebuilt aircraft began resembling something that might actually fly. The distinctive olive green camouflage had been recreated using available paint stocks, though the red circles marking Imperial Japanese Army Air Force service had been replaced with American stars and bars. Test instrumentation had been installed throughout the aircraft to monitor engine performance, structural loads, and control response during flight operations. Every system had been checked and double-checked, but fundamental questions remained about handling characteristics and structural limitations. The most troubling discovery came during structural testing of the wing assemblies. While the combat flap system was mechanically sound, the wing structure itself showed concerning stress patterns under simulated G-loading. Hairline cracks appeared in wing root attachments at loads that would be considered routine for American fighters. The extreme weight reduction that gave the aircraft its remarkable performance also created vulnerabilities that became apparent only under detailed engineering analysis. By late July, Project Phoenix was approaching completion, but the rebuilt aircraft represented more questions than answers. Its performance envelope was clearly extraordinary. Preliminary calculations suggested climb rates and turning capabilities that exceeded any Allied fighter below 20,000 feet. But the same design choices that created this performance also introduced structural limitations that could prove fatal under combat conditions. The aircraft was ready to fly, but whether it could survive the kind of high-G maneuvering that made it legendary remained an open question. Test pilot Bill Ferrier arrived at Eagle Farm on August 10th with orders to conduct the most dangerous flight evaluation of his career. The Psyche, rebuilt Japanese fighter, represented months of painstaking work and thousands of dollars in resources, but more importantly, it carried the hopes of Allied pilots who needed to understand their enemy's capabilities. As Ferrier walked around the aircraft for his pre-flight inspection, he was looking at either the key to Japanese air superiority or the most elaborate death trap ever assembled in an Allied hangar. The morning of August 17th dawned clear and still over Brisbane, with visibility unlimited and winds calm, perfect conditions for the most dangerous test flight in Pacific theater history. Bill Ferrier had spent the previous 3 days studying every technical drawing, every structural analysis, and every engineering note from Project Phoenix, but nothing could truly prepare him for strapping into the cockpit of a resurrected enemy fighter. At 0730 hours, he began his pre-flight inspection with the methodical precision that had kept him alive through dozens of experimental aircraft evaluations. The rebuilt Ki-43 sat on the Eagle Farm tarmac like an artifact from an alien civilization, its olive green camouflage and unfamiliar proportions marking it as fundamentally different from any Allied aircraft. Ferrier worked his way around the airframe systematically, checking control surface movement, engine cowling security, and landing gear condition. The fabric-covered control surfaces felt solid under his hands, but disturbingly light compared to the metal construction he was accustomed to. Every component had been rebuilt to Japanese specifications, but using available Allied materials and manufacturing techniques that might not match original tolerances. The cockpit interior reinforced the impression of entering a completely foreign technological environment. The instrument panel layout placed engine gauges in unfamiliar positions, while the control stick and rudder pedals required different hand and foot positions than American aircraft. Most unsettling was the complete absence of armor protection. No bulletproof windscreen, no back armor, no protective plating around critical components. Japanese pilots apparently accepted vulnerability as the price for maximum performance, a trade-off that went against every principle of Allied fighter design. Engine start at 0800 hours proceeded smoothly, the Nakajima Ki-43 radial settling into a steady idle that sounded remarkably similar to American power plants. But as Ferrier advanced the throttle for run-up procedures, subtle differences became apparent. The engine responded more quickly to throttle inputs than he expected, while carburetor heat application produced temperature changes that suggested different internal airflow patterns. Every system required conscious adjustment to unfamiliar operating characteristics. Taxi tests revealed the first hint of the aircraft's unique handling qualities. The lightweight construction made it remarkably responsive to control inputs. Slight rudder pressure produced immediate directional changes that required constant correction to maintain straight-line taxi operations. Ground handling characteristics suggested an aircraft designed for pilots with hundreds of hours of type-specific training rather than the standardized approach favored by Allied air forces. Takeoff at 0815 provided an immediate demonstration of performance that Allied intelligence reports had failed to capture accurately. The Ki-43 lifted off after a ground roll of less than 800 feet, climbing at an initial rate that exceeded 2,000 feet per minute. Within 3 minutes of leaving the runway, Ferrier had reached 8,000 feet altitude, a climb performance that surpassed any Allied fighter in service. But the same lightweight construction that enabled this remarkable climb rate also transmitted every air current and turbulence directly to the pilot, creating a flying experience that felt more like riding a bicycle than operating a military aircraft. Level flight characteristics at 8,000 feet revealed both the aircraft's greatest strengths and most concerning weaknesses. Cruise speed at 75% power indicated approximately 280 miles per hour, respectable but not exceptional by Allied standards. But when Ferrier deployed the combat flaps and entered a turning engagement, the aircraft's true capabilities became apparent. With flaps extended 30 degrees, the Ki-43 could maintain controlled flight at airspeeds below 90 miles per hour, while executing turning circles that seemed to defy aerodynamic principles. The combat flap system transformed the aircraft's handling characteristics so dramatically that it felt like flying a completely different machine. Stall characteristics virtually disappeared, replaced by machining flight that allowed continuous turning at angles of attack that would put any Allied fighter into unrecoverable spins. Turning radius decreased to less than 800 feet while maintaining positive G-loading, enabling tactical maneuvers that Allied pilots had described as impossible. For the first time, American intelligence officers could understand how Japanese pilots were achieving their legendary combat performance. But sustained maneuvering at these extreme flight conditions began revealing the structural limitations that engineering analysis had predicted. During a series of high-G pullouts from simulated diving attacks, Farrier felt concerning vibrations through the control stick that suggested airframe stress beyond design limits. Wing flexing became visible from the cockpit during maximum rate turns, while the fabric covering over control surfaces showed wrinkle patterns that indicated structural distortion. The same design choices that created extraordinary maneuverability also introduced vulnerabilities that became apparent only under sustained combat. Maneuvering. Mock dogfights against a Spitfire Phi flown by squadron leader James Mackenzie demonstrated both the rebuilt aircraft's tactical advantages and fatal flaws. Below 15,000 feet, the Ki-43 could outturn the Spitfire so decisively that Mackenzie found it impossible to maintain a firing position during turning engagements. But whenever Farrier attempted to exploit this advantage through sustained high-G maneuvering, structural limitations forced him to reduce loading or risk catastrophic airframe failure. The most revealing moment came during a simulated head-on attack when Farrier pulled maximum G-loading to avoid Mackenzie's mock firing pass. The airframe responded initially, but at approximately 4.5 Gs, alarming creaking sounds from the wing roots forced him to immediately reduce loading and terminate the maneuver. Post-flight inspection revealed stress cracks in wing attachment fittings that confirmed engineering predictions about structural limitations under combat conditions. Landing characteristics proved equally illuminating about Japanese design philosophy. The Ki-43 touched down at less than 70 miles per hour and rolled to a stop in under 600 feet, performance that would allow operations from improvised airstrips that could never accommodate Allied fighters. But ground handling required constant attention to prevent ground loops, while the lightweight construction made the aircraft vulnerable to crosswinds that would pose no challenge to more robust Allied designs. Farrier's post-flight report summarized the fundamental contradiction at the heart of Japanese fighter design: extraordinary performance achieved through sacrificing structural margins that Allied engineers considered essential for combat survival. The rebuilt Ki-43 could execute maneuvers that no Allied pilot had believed possible, but it accomplished these feats by operating closer to structural failure than any American aircraft would be permitted to fly. It was, in Farrier's memorable phrase, like flying a paper airplane, incredibly maneuverable, but liable to disintegrate under the kind of punishment that Allied fighters were designed to absorb routinely. The C-54 transport carrying the rebuilt Ki-43 touched down at Wright Field on September 23, 1943, beginning the most comprehensive enemy aircraft evaluation in American military history. Colonel Harold Watson, commanding officer of the USAAF Test Training Unit, had assembled a team of test pilots and engineers specifically to extract every tactical advantage from what intelligence reports now confirmed was the Nakajima Ki-43 Oscar, the mystery fighter that had been carving up Allied formations across the Pacific Theater for nearly 2 years. Wright Field's test facilities represented the pinnacle of American aeronautical engineering, with wind tunnels, structural testing equipment, and instrumentation capabilities that dwarfed anything available in the Pacific Theater. The Oscar would be subjected to systematic evaluation that would reveal not just its performance characteristics, but the entire design philosophy behind Japanese air power. Major Robert Strobel, the field's senior test pilot, approached the project with the kind of analytical precision that had made Wright Field the world's premier aircraft testing facility. The first phase of testing focused on baseline performance measurements that would establish definitive numbers for speed, climb rate, service ceiling, and range. Strobel's initial flights confirmed Farrier's observations about extraordinary climb performance. The Oscar reached 20,000 feet in under 8 minutes, a rate that exceeded the P-51 Mustang by nearly 2 minutes. Maximum speed at optimum altitude measured 308 miles per hour, respectable but not exceptional compared to contemporary Allied fighters. But these raw numbers failed to capture the aircraft's true tactical significance. Structural testing revealed the engineering compromises that enabled the Oscar's remarkable agility. The entire airframe weighed just 3,200 pounds empty, 1,500 pounds lighter than a comparable American fighter. This weight reduction had been achieved through systematic elimination of everything Japanese engineers considered non-essential: armor protection, self-sealing fuel tanks, redundant control systems, and robust structural margins. The result was an aircraft that existed in a constant state of engineering tension between performance and survivability. Wind tunnel testing at Wright Field's 7x10-foot facility provided the first scientific analysis of the Oscar's unique combat flap system. When deployed during turning maneuvers, the butterfly flaps increased the wing's coefficient of lift by 37%, while maintaining attached airflow at angles of attack that would stall conventional wing designs. This explained how Japanese pilots could execute sustained turning maneuvers at airspeeds that Allied pilots considered impossible. The system represented genuinely innovative aerodynamics that Western designers had never seriously considered. But the same wind tunnel test that revealed the flap system's effectiveness also confirmed its structural vulnerabilities. At airspeeds above 250 miles per hour, flap deployment created wing loading that exceeded design limits by significant margins. The system was brilliant for low-speed turning combat, but potentially catastrophic if deployed during high-speed engagements. Japanese pilots apparently had to choose between maneuverability and structural integrity depending on tactical circumstances. Armament analysis revealed another fundamental difference in design philosophy. The Oscar's two 7.7mm machine guns carried 450 rounds each, enough ammunition for approximately 45 seconds of sustained firing. By comparison, American fighters typically carried enough ammunition for less than 20 seconds of firing, but delivered that firepower through 6 or 8 50 caliber guns that generated 5 times the destructive capability per second. Japanese pilots were expected to achieve victories through precise marksmanship rather than overwhelming firepower. Engine testing of the Nakajima Ki-43 power plant revealed sophisticated manufacturing techniques that contradicted intelligence assessments of Japanese industrial capabilities. Cylinder tolerances were actually tighter than American standards, while metallurgy analysis indicated advanced alloy compositions that suggested access to strategic materials that Allied intelligence believed Japan lacked. The engine produced 925 horsepower through supercharging technology that matched or exceeded American designs in several key areas. Range testing provided crucial intelligence about Japanese operational doctrine. With internal fuel capacity of 158 gallons, the Oscar could operate at combat radius of approximately 400 miles, sufficient for defensive operations over Japanese-held territory, but inadequate for the kind of long-range escort missions that Allied fighters were increasingly required to perform. External drop tanks extended range to over 800 miles, but only when carried at the expense of combat maneuverability. The most revealing tests involved systematic comparison with Allied fighters under controlled conditions. Against the P-40 Warhawk, the Oscar demonstrated clear superiority in climb rate, turning radius, and low-speed maneuverability. But the Warhawk's superior diving speed, structural strength, and firepower provided tactical options that could neutralize the Oscar's advantages if exploited correctly. Against the newer P-51 Mustang, the performance gap widened dramatically. The Mustang's speed advantage was so overwhelming that it could engage and disengage at will, rendering the Oscar's superior turning ability tactically irrelevant. Pilot interviews with captured Japanese aviators, conducted through interpreters at Wright Field's intelligence facility, provided insights into training methods and tactical doctrine that complemented the technical analysis. Japanese pilots received an average of 400 hours of type-specific training before combat deployment, nearly double the training time allocated to Allied pilots. This intensive preparation was apparently necessary to safely operate aircraft that required exceptional skill to exploit their performance advantages without triggering structural failures. The interviews revealed that Japanese pilots were acutely aware of their aircraft's limitations and had developed tactical methods to minimize exposure to Allied firepower advantages. Standard doctrine emphasized hit-and-run attacks that exploited the Oscar's climbing ability, followed by disengagement before Allied fighters could bring superior firepower to bear. Sustained dogfighting was discouraged unless Japanese pilots held overwhelming numerical advantages or favorable altitude positions. By November, comprehensive testing had produced a classified report that fundamentally changed Allied understanding of Japanese air power. The Oscar represented a coherent design philosophy that prioritized pilot skill over aircraft durability, creating weapon systems that were extraordinarily effective when operated by experienced aviators, but catastrophically vulnerable when flown by replacement pilots with inadequate training. The aircraft's legendary maneuverability was real, but it came at the cost of structural margins that Allied engineers considered essential for combat survival. The final assessment concluded that Japanese fighter design represented brilliant adaptation to resource constraints and cultural preferences, but also revealed fatal vulnerabilities that Allied pilots could exploit through proper tactical application. The Oscar could outturn any Allied fighter, but it couldn't outrun them, outdive them, or survive the kind of battle damage that American aircraft absorbed routinely. Understanding these limitations would prove crucial as the war entered phases where Japanese training advantages began eroding and Allied industrial superiority started determining combat outcomes. The intelligence from Wright Field began reaching frontline squadrons in early 1944 through classified tactical bulletins that transformed how Allied pilots approached aerial combat. Captain James Watkins of the 9th Fighter Squadron received his copy of Technical Intelligence Bulletin No. 47 on March 15th while his P-38 Lightning unit was stationed at Dobodura Airfield in New Guinea. The document's clinical language couldn't disguise the revolutionary nature of its contents. For the first time, Allied pilots had systematic intelligence about their most dangerous enemy. Watkins had lost 3 wingmen to Japanese fighters during his previous combat tour, each a death attributed to the mysterious maneuverability that allowed enemy aircraft to outturn anything the Allies could field. The new intelligence revealed that these impossible maneuvers came at a steep price, structural limitations that made Japanese fighters vulnerable to tactics that exploited their weaknesses rather than challenging their strengths. The key was abandoning traditional dogfighting doctrine in favor of hit-and-run attacks that used superior Allied speed and firepower. The tactical revolution began with a fundamental shift in engagement philosophy. Instead of trying to outturn Japanese fighters, Allied pilots were instructed to use their aircraft's superior diving speed and structural strength to engage at high speed, fire brief bursts, and immediately disengage before Japanese pilots could respond with turning maneuvers. The P-38's twin-engine design provided both the speed advantage needed for these tactics and the firepower necessary to achieve quick kills during brief engagement windows. Watkins implemented the new doctrine during a patrol mission over Huon Gulf on August 2, 1944. His 4-ship formation encountered 12 Japanese fighters at 15,000 feet, a numerical disadvantage that would have been catastrophic under traditional tactics. But instead of accepting turning combat, Watkins led his flight in a high-speed diving attack that exploited every advantage the Wright Field analysis had identified. The Lightning formation dove through the Japanese formation at over 400 miles per hour, each pilot firing 2-second bursts from their concentrated nose-mounted armament. The results validated months of systematic intelligence work. Watkins destroyed 2 Oscars during the initial pass, watching both aircraft disintegrate under the concentrated fire from 450 caliber machine guns and 120 mm cannon. His wingman, Lieutenant Robert Chen, scored hits on a 3rd Oscar that immediately began trailing smoke and losing altitude. Most importantly, the Japanese formation's attempts to respond with tight turning maneuvers only confirmed their inability to effectively engage fast-moving targets that refused to participate in traditional dogfighting. The engagement's most revealing moment came when the remaining Japanese fighters attempted to climb back to altitude after the Lightning formation's initial attack. 3 Oscars pushed their engines to maximum power in steep climbing turns, but the Wright Field intelligence had predicted this tactical response. At approximately 4,000 feet per minute climb rate, 2 of the 3 Japanese aircraft suffered what appeared to be structural failures, their wings folding upward in the characteristic pattern that indicated G-force loading beyond design limits. Chen later described watching one Oscar attempt a maximum rate climbing turn, only to have its port wing separate completely from the fuselage. The aircraft tumbled out of control while the pilot attempted unsuccessfully to bail out of the disintegrating airframe. It was exactly the kind of structural failure that Wright Field testing had identified as inevitable when Japanese pilots pushed their aircraft beyond carefully calculated performance envelopes. The tactical success at Huon Gulf spread rapidly through Allied fighter squadrons as pilots shared intelligence about effective engagement methods. The 58th Fighter Group in China began using similar hit-and-run tactics against Japanese formations over the Yangtze River Valley, achieving kill ratios that reversed earlier trends. British Spitfire units in Burma adapted the doctrine to their aircraft's capabilities, using superior diving speed to offset the Oscar's turning advantages. Australian P-40 units in the Southwest Pacific found they could finally engage Japanese fighters on favorable terms by refusing turning combat and exploiting structural limitations. The intelligence proved equally valuable in training replacement pilots who no longer faced the psychological challenge of fighting an apparently invincible enemy. Flight schools in the United States began teaching specific anti-Oscar tactics that emphasized speed and firepower over traditional air-to-air combat maneuvers. New pilots arrived in combat theaters with systematic knowledge of Japanese fighter capabilities and limitations rather than the folklore and speculation that had characterized earlier training programs. By late 1944, the tactical revolution was producing measurable results across all Pacific Theater combat zones. Japanese Oscar units that had previously achieved kill ratios of 3 or 4 to 1 were struggling to achieve parity against Allied formations that refused to fight on Japanese terms. The 64th Sentai, one of the Imperial Japanese Army Air Force's most experienced Oscar units, reported losing 17 aircraft while claiming 25 Allied fighters during October and November operations over the Philippines, a ratio that represented tactical defeat for a unit that depended on numerical efficiency to offset industrial disadvantages. The psychological impact on Japanese pilots became apparent through intercepted radio communications and captured documents. Veteran pilots who had dominated Pacific skies during 1942 and 1943 found themselves unable to exploit their aircraft's legendary maneuverability against opponents who understood and avoided Japanese tactical strengths. Replacement pilots, lacking the extensive training that earlier Japanese aviators had received, proved catastrophically vulnerable to Allied pilots who could exploit Oscar structural limitations through systematic tactical application. The most tragic confirmation of changing tactical dynamics came through Japanese training accidents that mirrored combat structural failures. Flight schools in Japan reported increasing numbers of training aircraft lost to wing failures during advanced maneuvering exercises. Inexperienced pilots, attempting to duplicate the tight turning maneuvers that had made the Oscar legendary, were pushing lightweight airframes beyond structural limits that veteran pilots had learned to respect through years of careful experience. Intelligence reports from captured Japanese maintenance personnel revealed growing awareness within enemy units that their aircraft's greatest tactical advantages were becoming liabilities under changing combat conditions. Ground crews were reporting increased structural inspections and reduced authorized G-loading limits that effectively neutralized much of the Oscar's performance envelope. The same design philosophy that had created Japan's early air superiority was adapting poorly to prolonged combat against opponents who understood its fundamental limitations. The intelligence revolution that began with Lieutenant Gesell's wreckage analysis at Buna airfield had fundamentally altered the tactical balance in Pacific air combat, transforming the mysterious Oscar from an invincible opponent into a well-understood enemy whose capabilities and vulnerabilities could be systematically exploited through proper application of Allied technological advantages.